let's take a look at capacitors. So a capacitor is a pair of parallel plates separated by insulating material or vacuum. And we can draw a capacitor like so. Here's the two parallel plates with wires coming off of them. And in fact, this is the symbol of a capacitor in a circuit. So if we had a circuit, a DC circuit, containing a battery and a capacitor, it would look like this. And let's think about what would happen in terms of the electrons here. Well, electrons would be leaving the battery on this side, and electrons would be going into the battery on this side. So the electrons coming out of the battery would collect on this plate in the capacitor, and this plate of the capacitor would develop a negative charge. And then on the other side, we would have electrons being drawn out of that plate, and so a positive charge would develop on this side of the capacitor. So a charge, an equal and opposite charge, would develop on either side of the capacitor. Because of this, we also get an electric field inside of the capacitor. The electric field inside of the capacitor between the plates would point from the positively charged plate toward the negatively charged plate. Now, this development of charge on either side doesn't happen instantaneously. It develops over time. And let's think about that. So, in the beginning, when there's no charge on the capacitor, the battery is sending electrons out of this side and bringing electrons into this side. And the capacitor, without any charge on it, is just allowing that to happen. A little bit later on, once a little bit of negative charge is developed on one side and a little bit of positive charge is developed on the other side of the capacitor, now it's a little more difficult for the battery to send those electrons in. The electrons are going to resist developing on that plate because that plate already has a negative charge on it. The battery is attempting to send more electrons onto an already negatively charged plate, which the electrons are going to resist. Also, on the positive side of the capacitor, the battery is attempting to pull electrons away from that positively charged plate, but those electrons are attracted to the positively charged plate, so it's more difficult for the electrons to be drawn out of that side. So at this point, in this picture, it's more difficult for the electrons to flow. The current is going to be smaller at this point. Much later, when there's a lot of negative charge on the negatively charged plate and a lot of positive charge on the positively charged plate, well, at that point, the battery is not going to be able to send any more electrons onto the negatively charged plate. There's going to be so much negative charge that the battery will not be able to push more electrons onto that negatively charged plate. And likewise, on the positive side, the battery is not going to be able to pull any more electrons off of that plate because there's so much positive charge attracting those electrons. So much later on, no charge is going to flow. There's not going to be any current anymore. Now, every capacitor has what's called capacitance. The capacitance is defined as the charge per potential difference on a capacitor. And so we can write an equation for that. Capital C, the capacitance, is equal to Q over V, where Q is the charge on a plate, and V is the potential difference across the plates. And the unit of capacitance, as you can see, is the coulomb per volt, and that's defined as a farad, capital F, named after Michael Faraday, same Faraday as Faraday's law. And most capacitors have capacitances that are measured in microfarads, or nanofarads, or even picofarads. We can write down the energy that's stored on a capacitor this way. The energy stored is equal to 1/2 CV squared, where C is the capacitance of the capacitor, and V is the potential difference across the plates. Now, if we have a regular old capacitor that's made out of two parallel plates, with vacuum between them, then the capacitance is given by this expression. C is equal to epsilon naught A over D, where A is the area of a plate, and D is the distance between the two plates. Epsilon naught here is a constant, known as the permittivity of free space. It's in your data booklet. Now, if we make a capacitor that isn't separating the two plates with vacuum, but is instead separating the plates with some kind of material called a dielectric, then the expression becomes C is equal to epsilon A over D, where epsilon is the permittivity. And every substance has a different permittivity. So if we had a capacitor with two plates separated by plastic, the plastic material has a certain permittivity associated with it. Or if we separated it with another insulating material, like, say, wood would have a certain permittivity. Now we can imagine capacitors connected in different ways, and it turns out that if you connect capacitors in series, then their total capacitance is given by this expression. Likewise, if we connect capacitors in parallel, the total capacitance of that combination is given by this expression. And if those expressions remind you of something, they probably should. They are similar to, but the opposite of resistors. If you remember way back when we talked about resistors in parallel, that was this reciprocal type expression, and resistors in series, it was just the sum. I'm not going to get into why exactly this happens right now, but it is an interesting idea. So let's look at charging up a capacitor. We already looked at this a little bit, but over time, if we have a battery connected to a capacitor, charge will build up on the plates. And at first, that charge is going to build up quickly. But then, as it builds, the charge is going to build up more and more slowly because the plates already have charge on them. So in other words, the rate that the charge develops or builds on the plates will be decreasing as time passes. It'll be decreasing as more and more charge is already on the plates. And so we can sort of sketch a graph of this. The charge that develops on the plate over time would look a little bit like this. It will increase pretty rapidly at the beginning, but then as time goes by, the amount of charge that's being added to the plate will decrease. It's getting harder and harder for the battery to put more charge on the plates. And eventually, it will reach a maximum. We'll call it Q max. So that's the maximum amount of charge that can be put on the plate by that battery. Now, this corresponds to the current, so let's think about the current and what that would look like over time. So at first, there's going to be a large current because the charge is going to be flowing rapidly onto the plate. But over time, the current is going to decrease, and it's going to eventually, at the end, become approximately zero because no more charge can be put onto that plate. Very little charge will be flowing onto the plate. And if we wait until an infinite amount of time has passed, no more charge can be added, so the charge on the plate reaches its maximum value, and when that happens, the current at that infinite time approaches zero. Now let's think about discharging the capacitor. Well, if we start out with a charged capacitor and then connect it to a resistor, like this, then that charged capacitor will at first lose the charge rapidly because the charges on those plates are repelled by the plates themselves. There's going to be a large potential difference across the plates that's driving the current. Now later on, there's going to be less charge on those plates because the charge has flowed. So when there's less charge across the plates, there's less potential difference across the plates, and there's going to be a smaller current. And then much, much later, all of the charge has left the plates and there's no more current flowing. So, in other words, we can kind of sketch the graph for this. At first, there's a lot of charge on the plates, and the initial charge, we'll call it Q0. And then over time, the charge decreases. So at first, it decreases rapidly as the charge moves rapidly away from the plates. And then over time, as the potential difference decreases, the charge is going to approach zero, but it's going to leave less and less rapidly. And the current would do a similar thing. At first, the current is going to be large as the current flows quickly, and then the current will decrease and decrease and decrease. And same with the potential difference across the plates. At first, the potential difference is going to be large, but it will decrease. And we can write expressions for the charge, current, and potential difference across the plates in this way. Turns out they're decaying exponential functions. And when we write them this way, we use this tau, this expression tau. Tau is equal to R times C in this situation, where R is the resistance in the circuit and C is the capacitance of the capacitor. Now, I mentioned before in the last topic we covered that capacitors can be included in rectifiers. This will smooth the rectification. It will make the change from AC to DC be a little more smooth rather than what we saw with full wave rectification. And I'll show you an example of how we could do this. And it looks a little complicated. Maybe it's a little hard to understand exactly how it works. There is a Fallstad simulation that I would suggest using, and I'll link it in the description of the video for you to go play around with that. But the effect of the capacitor is to smooth the rectification. And I'll draw an example here. So here is the oscillating AC potential difference coming from the generator. And then I'll draw what we would get if we had this without the capacitor. Then it would be full wave rectification. But with the capacitor, we get this smooth potential difference, which is not exactly direct current, but it's certainly closer to direct current than we would have without the capacitor.